Good.
I hope everybody loaded up on their coffee for tonight's talk. I did, so we'll see how this goes. All right, okay, this works, that's good. Okay, so yes, as Loren noted, this is my topic today on doing a site response analysis approach and tweaking it from what we've been doing in the past so that it's compatible with the new NBC 2020 seismic hazard model. So what I want to start the presentation is in order to understand the sort of fundamental differences between how amplification was treated in NBC 2015 compared to the new NBC 2020 approach. We're going to look at the differences between aggregated hazard that you get from the seismic hazard calculator versus what we're going to call event scenario hazard that we can examine looking at deaggregation data. So these fundamental differences between NBC 2020 and 2015 really come down to the way that nonlinear amplification is treated. So in NBC 2015, it's all done according to the aggregated probabilistic PGA value, whereas in the sixth generation seismic hazard model of Canada that's now being used for NBC 2020, the nonlinear amplification is done according to a median ground motion intensity for each individual event scenario that's considered in the hazard model. So we're going to take also a look at the probabilistic distribution of these event scenario hazard values, which we can look at using the deaggregation data from NBC 2020. So this is something that we haven't been able to really look at previously. And then I'm going to really briefly touch on, which should be review, hopefully for most people here, on the current practice for doing seismic site response analyses using the NBC 2015 approach. And then I'm going to spend the rest of the talk really presenting this study that we've been doing, looking at implementation of SSRA results inside the sixth generation seismic hazard model. And then we're going to compare those results to what we would get from simplified methods, where we calculate uniform hazard response spectra using site response analysis results in a way that's going to be compatible with what how amplification is treated in NBC 2020. So this is an example of just what we would be getting from the 2015 hazard calculator. So we have a suite of spectral accelerations here for various periods, right? And these, in this red box here, this is what forms what we call the uniform hazard response spectrum. So basically, these are values at every period that have a 2% probability of exceedance in 50 years, right? And that can be converted to an annual probability of exceedance of 0.0004, which, take the reciprocal of that, that's a 2,475 year return period. So that is what we call an aggregated probabilistic hazard. Okay, and so just so we can keep our nomenclature clear here, when we're talking about our 50-year or the probability of exceedance in 50 years, we can do a conversion to annual exceedance rate. This is what we're calling your annual probability using this sort of formula right here. You may or may not have done that yourself. And then the return period is obviously the reciprocal of the annual exceedance rate. Don't confuse that with the average recurrence period of an actual earthquake event. Okay, so what the values that we use, or the hazard values we use for design, these UHRS values, they come from what we call a hazard curve. Okay, so this figure on the right, this is a hazard curve. So this is plotting the annual rate of exceedance of any particular value. Okay, so essentially for any value, any trial value, let's just say 0.2 G, what is the total annual rate of exceedance from all earthquake events that contribute to the hazard? Okay, so and then the way the model works is it looks at each possible PGA scenario and then calculates for an individual event what is the annual rate of exceedance of that event. It then adds up what the so when I say event, I'm talking about an event scenario. So this would be a scenario where an earthquake that has a certain magnitude and a certain source to site distance. That's what's going to generate a particular hazard value. So there's an expected value, and then there's a probability of exceeding whatever the trial value would be. So you can do 0.1 G, 0.15, 0.2, 0.25, 0.3. The model will look at every possibility and then say what's the annual rate of exceedance of that value, say 0.2 G, for every single event in the hazard model, and then add up all of those individual annual rates of exceedance to get a total annual exceedance rate for the total hazard. Okay, so that's how basically the curve here is actually generated, right? So then when you want say a 2% and 50-year probability exceedance, you just go to the annual rate of exceedance here, 0.00404. What's the value? Oh, in this particular example, it's 0.58 G, and this happens to be a Victoria example for a VS30 of 1100 meters per second for PGA. So we can get a better look at this, what I'm talking about here in terms of individual event scenarios, looking at some deaggregation data. So maybe some or many of you may have looked at this data in the past. So this is an example of a deaggregation plot from NBC 2015. This one happens to be PGA at 2% in 50 years. So what you're seeing here is on the horizontal axes, you've got distance on the one axis and magnitude on the other axis, and you've got bins that basically they look at what's the contribution to the total hazard value, in this case 0.6 G, from each of the event scenarios. So the event scenarios will occupy a bin in here, right? With a magnitude and a distance, okay? So the event or the event scenario contribution is basically just the ratio of the individual rate of exceedance for that event divided by the total annual exceedance rate for the total hazard. Okay, so in this case, what comes out to 2% per 50 years. So in the example here that we're looking at, we can look at the modal contribution. Okay, so this is the highest contributing contributor or event scenario. It has a magnitude of 8.95, so this is a subduction interface event at a distance of 50 kilometers. That's the midpoint of the bin. And the contribution to the total hazard is 4.8%. So if we look at that, what we can gather from that is that the annual exceedance rate for that particular event is going to be basically 5% of the 0.00, or basically 0.04%, right? So it's 1/20th of 0.04% or 0.002%. If you think about that in terms of return period, that's 52,000 years. Okay, so that is the biggest contributor to the hazard is an individual event with a return period of 52,000 years. So now to move on to how amplification is treated in NBC 2015, and this will be reviewed to, I'm sure, everybody in the room. But they're all based on probabilistic hazard values, the UHRS, the PGA, PGV, which are for a Site Class C reference ground condition. And then the amplification to get a uniform hazard value relative to Site Class C, you have an amplification factor which were published in the code, right? So those are a function of period, site class, and the PGA for that reference ground condition. So we're talking then about the PGA being an intensity measure for the purpose of determining nonlinear amplification effects. Typically that reference PGA was Site Class C. Certainly in the West here, it's usually Site Class C. In the East, it tends to be 80% of Site Class C. So that Site Class C value, that PGA value, is a probabilistic value coming from the aggregated hazard at the design hazard level. Okay, so these typical tables that we see published, you can pick off the appropriate f of t value, which is a function again of the aggregated or of the probabilistic PGAref, and then multiply that by your Site Class C hazard value, and you get your amplified value. So if we see what do these amplified factor or amplification factors look like, these FFT values, here is site class D, and this is just them plotted up. So you see in the different colors what the amplification function looks like for the different PGA values. So starting with 0.1 G in purple, and then you see the amplification factor is decreasing as the ground motion intensity increases, right up to 0.5 G in red, which is down here. Okay, so everything below this dashed line is de-amplification, everything above it is amplification. And if we go to site class E, we see a kind of similar shape, but more exaggerated. So higher amplification factors in the positive direction, and higher de-amplification below 1. So again, same trend, but more exaggerated, with 0.1 G amplification being way up here, and then decreasing significantly as PGA increases down to there. Now in 2020, in MEC 2020, the amplification is based on internal values, the amplification is all treated internally within the seismic hazard model, and it's calculated using each of the ground motion models that are included within the hazard model. So there are 4 ground motion models for each of the tectonic regime types that we have here in southwestern BC, and for each of those GMM values, what they're doing is they have a site term that uses VS30 to estimate the linear amplification. This is like the elastic site response. And then another site term that calculates the nonlinear modification of the linear amplification, which is based on the median prediction of a PGA. Typically, for most of the ground motion models, it's PGA for a rock ground motion value, and the intensity measure that's used is PGA of rock, and it's the median prediction of that ground motion value. So then what happens is for every single individual event scenario inside the model, they will calculate the amplification and then calculate an amplified hazard value, and then probabilistically combine all of the amplified hazard values. If we do a comparison between the amplification factors for 2020 and 2015, and to do this comparison, because they're not using site classes in the same way anymore, but we can use the VS30 values for site class D, which was 250 meters per second was the representative or characteristic shear wave velocity for site class D in 2015. So if we do the amplification as a response spectral ratio, RSR, response spectral ratio, that's just basically the ratio of the amplified spectral values divided by the spectral values for the reference ground condition, right? In 2015, that reference ground condition was site class C. So if we do site class D relative to site class C, we'll see the same amplification factors we just looked at previously, but I'm only looking at now in blue is a PGAref of 0.2 G, and in red is a PGAref of 0.5 G. So these guys down here are the 2015 values, and the ones with the black lines up here, the black chain dash lines, these are the 2020 values. And what you'll see is that short period at 0.2 G, they're about the same, right? At longer period, the 2020 values are a little bit higher. But when we go to 0.5 G, we see a much bigger difference. And what we see, the difference between the black outlined diamonds here and the red diamonds here, MEC 2020 is much higher for much higher intensity ground motions. So for PGAref 0.5 G, you're much higher now. And you see that the difference between 0.2 G and 0.5 G in MEC 2020 is not that big compared to in 2015. Same thing with site class E. If we do VS30 of 140 relative to VS30 of 450, we get these response spectral ratios. Again, for 0.2 G, very similar in the short period range, higher for MEC 2020 in the long period range, and then that difference becomes much more accentuated when we start looking at 0.5 G, right, where it's higher at all levels, or at all periods, sorry. So we can look at deaggregation data now from the 6th generation seismic hazard model of Canada using, so that hazard model is now being run on the OpenQuake platform, and that actually now allows it a much more informative deaggregation. So on the right, you can see the NBC 2020 deaggregation. This particular example is, again, Victoria PGA at 1100 meters per second and 2% and 50-year probability of exceedance. Okay, so the hazard value here, the aggregated probabilistic hazard value is 0.58 G in this case at 2% and 50 years. So we deaggregate that particular value, and this is the result we get. So it's not that dissimilar from what we saw before in terms of we have, again, magnitude on the axis down here. We got distance on this axis. So we have the bins, and we have the percent contributions, the towers in each of the bins. But now we have this rainbow colors. Okay, so this is actually allowing us to look under the hood of the hazard, the aggregated probabilistic hazard values. And what these colors are representing is the distribution of epsilon. So what's epsilon? Epsilon is the number of standard deviations between the natural logarithm of your aggregated hazard value. This is the one we've been using for design, right? The 2% and 50-year value, 0.58 G. Take the ln of 0.58 G in this case. And if you then subtract the number of sigmas that we get from this epsilon data, you'll get this mean value, or what the mean hazard value would be for either individual events. This is for individual events, or for the total hazard as a whole. Okay, so this mu, this is the mean. This is epsilon, gives you the number of standard deviations from the mean to get to your aggregated total hazard value. Okay, and just to point out, because this is all logarithmically distributed, as we're going to see in the upcoming slides, when we look at this mean value in logarithmic space, if we will take the inverse of that, and it's in linear space, we talk about the medians. When I talk about in future slides about the median and intensity level or median hazard value, that's basically coming, the ln of that gives us this mu value. Okay, so the sigma value is basically a measure, think of it as a standard deviation. It's the measure of aleatoric uncertainty that is within each of the GMMs prediction of that mu value, that average value. So they come up with a prediction of what the average would be, and then there's a certain amount of variability on that is due to aleatoric uncertainty, and the GMMs attribute that to event and site-to-site variability. So if we take a look at that same deaggregation data and just focus in now on this rainbow bar up here, this gives the percent, the distribution of percent contributions for each of the epsilon bins that are now in the deaggregation data. So if you get actually a data file, you'll see every magnitude and distance combination will have a distribution of epsilon. Okay, and when we look at the total hazard, this is giving us the distribution of epsilon for the total hazard. And if we look at the data, we can see up here the mean is 1.9. It's actually either 1.86 or 1.87, depending on the deaggregation data processing that you do. And so if we look at that distribution here, plotted up now, in terms of contribution to total hazard relative to the epsilon, you can see these purple bins, which are the kind of the coarse bins that the deaggregation data gives you. And the mean, the weighted contribution weighted mean of 1.87, that's basically the average or the mean right on this normal distribution that you see on the red curve. Okay, and just to show you the 0.58 G, which is the probabilistic hazard value, that is what corresponds to an epsilon of 0. So if you look here, epsilon of 0, it's basically where the green switches to an aquamarine, which is basically right down, appears right down near the bottom of this crustal hazard contributors and nowhere else. Okay, So this gives you a sense of basically how far all the individual events are from the actual probabilistic hazard value that we use for design, in this case 0.58G. We can also look at the mean epsilon for the individual scenarios, the three different tectonic regime types that we deal with. So if you go into the data, we pulled that out. We have a 44% contribution of crustal, 33% in-slab, 23% interface, and the mean epsilons we can figure out from that deaggregation data. So the sigma values, these are all specific to the actual GMMs. So these are a function of the publishers of the GMM model and their fit to the empirical data, right? That's how they generate the sigma values. So in the paper here by Michael Colai and the group at Enercan, they have published sort of plots of the variation of sigma with period for each of the three tectonic regime types. And then for the PGA, we got these values actually from UBC. So now that we can go back to that this equation right here. So this is basically the equation that you saw sort of previously, but now what we're doing is saying, okay, we want to actually calculate mu. We can calculate the mean using ln of the probabilistic hazard value we get from the hazard calculator, minus the mean epsilon that we can get from the deaggregation data times the mean sigma values that are associated with the GMMs. So this is, and then that mean is equivalent to the ln of the median, okay, which I'll show you in a second how that makes sense. So in this example that we were just looking at, here are the epsilon values that we just looked at for each of the three tectonic regime types, as well as the mean for the total hazard of 1.87. There's your sigma values, each of the individual averages of the 4 GMMs for each of these tectonic regime types, as well as the contribution weighted average for the total hazard. And then from those we can calculate median PGA values. So for crustal, it's 0.24G, for in-slab, 0.125G, for interface, it's 0.15G, and for the total hazard, the median is 0.175G, okay? These are the median values that we can use moving forward. So I promised you I would show you kind of how you can visualize the mean versus the median, okay? So if we look at the PGA distributed now and plotted as the ln of PGA, the probability density function you get using that mean, so we just looked at that was ln of 0.175G, with the sigma of 0.642 here, and plot the normal distribution, then this is what the distribution of the natural logarithm of the PGA looks like, okay? So in this space, in the logarithmic space, you'll see that the mean equals the median equals the mode, right? So this is your 50 percentile value, which is also the mean value. But now if you convert that over into just linear PGA, this is kind of the same data presented in linear PGA, and this is the purple one for the total hazard. You now see the shape of the log normal distribution. This is what you want us to visualize in your mind when you're actually thinking of hazard values. The probabilistic aggregated hazard value is this guy, 0.58G. It sits way out over here at the tail end of the probability distribution, okay? The median value sits right here at 0.175G. Compare that to the purple squares here, right? And this is basically, right, if you know probability density functions, 50% of the area lies to the left, or is less than 0.175G, and 50% of the area under the curve lies to the right, yeah? So now if we compare these median, we can actually, we can duplicate what I just did for PGA, and we can repeat that for all the spectral periods. Get the deaggregation data for all different spectral periods and construct the median response spectra, okay? So I've done that here. I've shown you, there's purple again. This is the total hazard median. And then each of the three source types, again, these are their median target spectra, okay? So if we just look at the purple one for the total hazard, compare that to the total hazard UHRS in black, and you can see how much of a difference there is, okay? So this is anywhere from 3 to 4 times higher, than what the median or the expected prediction coming out of the GMMs is, okay? So when we think about, the kind of geotechnical engineering we like to do, we like to think of factors of safety. Well, this is like a 3 to 4 times factor of safety on the expected values coming out of the GMMs, okay? And I'd like to go further by suggesting that you look at this scale. So this can be either your spectral accelerations or your PGA on the vertical scale. I want you to actually think about that as actually being, like this median, as being just 1 point on the probability density function. So this is the PGA probability density function. That's how you should want to think about all the possible contributions that should make up sort of a density, an area here that has a density. And as you go higher and higher, that density should get thinner and thinner and thinner until you get to the probabilistic UHRS that we use for design, which should be very thin. It's like stratosphere. Think of it like that, right? Like you come out of the clouds and you're in the stratosphere, okay? Now, okay, so that's the end of my theoretical chat about all of the guts of hazard values and the distribution of hazard values that we can now sort of get some look at. Think about taking the peel off of the orange, and we can now start to pull the slices of the orange apart, okay? We couldn't do that before. So now let's switch over to seismic site response analysis, okay? So what is seismic site response analysis for anyone that's not familiar? This is basically analysis that models the response of a multi-layered soil profile to upward propagation of horizontal shear waves during an earthquake, okay? So it's the response to an individual event. It's important. I want everyone to kind of realize that's what the analysis is. We're saying, how will the ground respond to a earthquake? And what we do is we look at the variability in response by doing multiple analysis on a whole suite of horizontal acceleration time histories, right? So typically what we'll do procedurally, we'll get those acceleration time histories that we select and we scale them to kind of match a target response spectrum that's representing a reference ground condition consistent with the conditions within a basal layer, which should, if this is done properly, behave as an elastic material throughout the whole intensity range for the ground motions that you're actually looking at, okay? So that's important, right? Ideally, it would be bedrock. I realize doing SSRA here in the lower mainland, where bedrock is like miles down, is more challenging. But the key being that whatever your basal layer is, it does need to be elastic, remain elastic at the ground motion intensities that you're analyzing, okay? So then what happens as you propagate the ground motions up through the various layers, the intensity and frequency content of those ground motions will be altered based on the dynamic soil properties that you assign to those layers. And it varies as a function of shear strain. So as the shear strain increases, your shear stiffness is going to decrease, and your hysteretic damping is going to increase. So when we're doing site response analysis in the sort of typical practice that we're doing using NBC 2015 hazard values, the procedure has generally been scale and oftentimes spectrally match these individual event time histories to a probabilistic target UHRS. That's our stratosphere kind of hazard values, yeah? And for whatever reference ground condition you've picked for your elastic base. And so yes, so these are going to be aggregated hazard values at the design hazard level that you're using for your analysis. Then you're going to conduct what is essentially a deterministic site response analysis, and you generate a suite of amplified response spectra, right? Typically then, though, that suite of amplified response spectra, the mean gets selected and that gets provided to the structural engineer for structural design. Now, a couple of problems with that approach. One of the problems with that particular approach is that the amplified spectral accelerations for any particular period are going to be like they're going to if the input motions were high at that period, the output is going to be high at that period. If the input motions are low at a particular period, then the output's going to be low, right? And that's why typically there's been a desire to create what I call the Franken earthquake, which is spectrally matching to a probabilistic uniform hazard response spectrum that has essentially zero probability of occurrence. Okay, so the fact that we're using amplified response spectra is why we're sort of wanting to do this thing that creates this beast that will never actually occur, because if you have a 2% probability of exceeding any particular hazard value, having an earthquake that has a 2% probability of exceeding all of those periods is pretty much like zero probability, right? So the other problem with this is the same problem that has been identified with 2015 in general, which is that by calculating your amplification based on, in this case, time histories that are scaled up to the aggregated probabilistic hazard, you're generating very high shear strains due to high ground motion values. Those large strains are inducing those large strains are causing a lot of nonlinearity in your ground motion, in your soil response. And then what that's doing is it's causing a lot of damping, right? So you're actually damping out a lot of the expected amplification by using such high aggregated hazard values. And this is the same problem that has been identified with the approach in 2015, where everything was based on site class C. That was the only probabilistic hazard value generated. So that was the basis for figuring out what the amplification factors were. So another method that would be similar to, or certainly consistent with MBC 2015, would be what's called the hybrid method, which Stewart et al. In 2014 had coined. And basically that's essentially what the MBC 2015 does, okay? So, but you're doing it for a site response analysis. So you're doing the same first two steps. You're getting your amplified spectral accelerations, but using the hybrid method, you would get an actual amplification function that goes with each of that's applicable to each of the earthquakes, which is basically just the ratio, your response spectral ratio between the amplified spectral values that come out of the analysis divided by the spectral the spectral accelerations of the input motions, right? So this is just generating f of t only for a site-specific analysis. And then in this hybrid method, what you would do is you would take that mean f of t for the whole suite and multiply that by the UHRS of your target spectrum that you used for scaling your motions in the first place, your input motions, right? And that will give you the amplified UHRS, okay? So this is completely consistent with the f of t approach in MBC 2015, but it still suffers from that same problem, is that the time histories that you put into your analysis have been scaled to this extremely high aggregated probabilistic response spectrum. So for MBC 2020, if we're going to do SSRA that are consistent with what the 6th generation seismic hazard model, we did a study that was done in cooperation, Thurber Engineering, in cooperation with the Earthquake Engineering Research Facility at UBC. This was a study that was peer-reviewed by Golder WSP and funded by EGBC. And the purpose was to investigate how we can implement site response analysis into an MBC 2020 framework for specifically, in this case, for structural analysis of seismic retrofits for the BC schools in accordance with the 2020 edition of the Seismic Retrofit Guidelines. So the objectives of this particular study were, one, to incorporate the SSR results directly into the seismic hazard model, which allows a probabilistic computation of the amplified UHRS. So this we're referring to as the rigorous method, which we're going to look at here next. And then to compare that to the amplified UHRS we would get using simplified methods. And the two methods that we looked at in this study, one was the hybrid method I just described, and the other is the modified hybrid method, both of which were described in this peer report, guidelines for performing hazard consistent one-dimensional ground response analysis for ground motion prediction. Okay, this is by Stewart and company. So I want to pause before I jump into the results of the study to just acknowledge the contributions of my colleagues at Thurber, Mackenzie Douglas and Paul Wilson, and at the UBC, Armin Benbenzadeh, and I apologize if I stumbled over your name, Armin, Mike Fairhurst and Carlos Ventura, and at Golder WSP, it was Roberto Oliveira, who's been doing the peer review, Peter Mitchell at EGBC, and at NRCan, Michael Kolai and Stephen Halchuk, Michael Kolai in particular, who's been very patient with me, Graham Taylor at TBG Seismic Consultants, and Tuna Owner, who a lot of this, the idea for this is kind of sort of hatched out of discussions with her. So the particular site, we used one site to run for this pilot study. And this was basically ground conditions that we had already characterized at the legislature in Victoria. So this was a 9.1 meter deep bedrock scenario. The average time-weighted average shear wave velocity so this is Victoria clay overlying bedrock with a time-weighted average shear wave velocity of 166 meters per second. The fundamental period of the soil column is 0.22 seconds. And you can see here, both looking at the shear wave velocity profile and the undrained shear strength profile, that this is a very stiff to hard desiccated crust down to about 5 meters deep over top of a stiff clay with a minimum dynamic undrained shear strength of around 60 kPa, and then jumping up to bedrock, which for this study we used 1100 meters per second to characterize the shear velocity of the rock. So in the rigorous method, what we did, and I'll show you in the next few slides the visuals, but to walk you through the methodology, we scaled the earthquake time histories to various PGAref. Okay, these were not connected directly to any probabilistic hazard level, but they were representing a range of median PGA kind of within this probability density function, right? So the spread of possible scenarios that are considered based on all the events in the seismic hazard model. So we conducted deterministic site response analysis. These weren't probabilistic, it was deterministic. And we generated a suite of amplification factors which are conditioned on these different reference PGA levels. And we did that for each tectonic regime type, each of the three source types. We then, UBC, we gave those suites of amplification functions in tabular form to UBC, and they replaced the site terms that are in the GMMs in the model with lookup tables of these average FFT values, and they were all source tectonic regime type or source specific. Okay. Then they ran the hazard model, so it then computes the amplified response spectra for each individual event scenario, right, as a function of these amplification functions, and then basically aggregates all of those to get your amplified value. Okay, so just like what I described earlier, that these are basically, the GMMs are looking to the median prediction of PGA for typically rock PGA, and then saying, okay, depending on what that median intensity level is, I'm going to come and look up and get the right FFT value that goes with that predicted PGA, median PGA for the individual events. And then UBC generated the hazard curves using those amplified values, and then we construct the uniform hazard response spectra for different hazard levels using the hazard curves. So this is when the time histories were all selected by UBC. and they were selected based on the shape of the 2% and 50-year UHRS for the individual tectonic. So not 2% 50-year total hazard, but for each of the tectonic source types, the 2% and 50-year hazard for those sources. There was a target spectrum, and then the earthquakes were picked so that the geomean of those would fit as well as possible the target spectrum. And then when they gave us those time histories, we scaled each suite to these 5 different PGA levels. So 0.05G, 0.1G, 0.2, 0.4, and 0.6G. Okay. This is just an example here of what it looks like for the time histories all scaled to 0.2G for the 3 different source types. So no spectral matching, just scaling. Okay, so now we input those into our site response analysis, and we develop the amplification functions. Okay, so these are now specific to each PGA level. So in this particular example, we're looking at 0.1G PGA, and this is the example for the in-slab suite of time histories, so 11 time histories. And you can see the amplification factor plotted, fairly consistent results, particularly around the natural period of the site, with a bunch of extra noise at the very short period or high frequency domain. If we look actually at the coefficient of variation, what's interesting, if you compare the coefficient of variation, that's the standard deviation divided by the mean for the suite of 11. The black is the input response spectra. So because we scaled the PGA, we have the lowest coefficient of variation at 0.01 seconds, and then it kind of increases a fair bit as we go to longer periods, right, further away from our scaling point. The amplified response spectrum, which is what you get directly out of the site response analysis, was very closely, like once you get away from the PGA here, where it's higher than the input, once you get out to about 0.05 seconds and beyond, it very closely matches the input. So this is the problem that everyone's been trying to get around by using spectral matching, is to say, that's too much variability, and so we're going to spectral match. But it actually turns out that if you calculate the amplification, the site is such an effective filter for certain frequencies that you end up with quite low coefficient of variation outside of the very short period range, which is not really of much structural significance, right? So, and even though we scale the PGA, it gets even lower as you get to longer periods because you're getting further away from the fundamental period of the site. So here's just a visual of the 5 different intensity levels that we did. And as well, so at each of those intensity levels, we did nonlinear analysis, but we also did a linear analysis at 0.05G. So this is giving you your purely elastic response. Okay, what I want to point out on this slide is that if you look at the 3 tectonic source types, the amplification functions are almost identical, with the exception of, again, that sort of noisy short period range. And then right at the very peak around for an elastic response, there's a little bit of variability, but otherwise very consistent. Okay. So now if we look at those means for each of the intensity levels all superimposed, we get to see what actually happens in a soft soil site as a function of increasing intensity. Okay. So the purple curve here, this is your linear response if you had an elastic material. So it's peaking right at 0.22 seconds, which, as I said before, is what we would predict using 4H over VS, right? And very sharp. So this is a resonance site. Peak amplification here is about 4.7 times what it is with the ground motion on rock. Then we go to colors from blue to green to gold, orange, and red, and this is increasing PGA. Blue 0.05G, green is 0.1, orange 0.2, gold 0.2, orange 0.4, and red 0.6. So what you can see here is that there's a heck of a big difference between your linear response and your nonlinear response at 0.6 G. Okay, so this increasing ground motion intensity, PGA in this case, causes an increase in your shear strain, causes a decrease in your shear stiffness, causes an increase in damping, and then you see the result of all that is a reduction, a very strong reduction in your peak amplification, and a shift to longer period. Okay. Yeah, so think about the aggregated probabilistic hazard for this site, for rock, is 0.58 G. So that's almost identical to this red 0.6 G scenario, okay? And remember that the median hazard value for this was 0.175 G. So you expect it to be a little above this gold. So that's going to be the difference between doing a median-based analysis and the probabilistic. So we'll see that in these coming slides. So the purple curve here, this is our reference UHRS for VS30 of 1100 meters per second. The orange is the amplified UHRS you would get assigning a VS30. So I forgot to mention on the previous slide, the VS30 for this site, if we believe that was relevant, would be roughly 410 meters per second. Okay, this is basically 166 over 1100, 9 meters of 166 over 21 meters of 1100 meters per second. The blue is the probabilistic UHRS that we generate by incorporating all of those F of T values, the PGA dependent F of T values, into the hazard model. So this is our probabilistic amplified UHRS using this rigorous method. Okay, what you can see here is at 0.3 seconds, we are much higher than what would be predicted using a VS30 type approach, because this is a resonant type high impedance site generating resonant ground motion amplification. So we also wanted to look at some simplified methods. So specifically the modified hybrid method described by in that peer document. Essentially what you're doing in this case is you're calculating the amplified response spectrum by taking the amplification function, just like in the hybrid method, multiplied by the UHRS of your reference ground condition. But the difference now is the amplification function is conditioned not on the probabilistic value of 0.58 G, but on the median PGA value, okay? In this case, for total hazard, 0.175 G, this guy down here, right? So, and to remind you that median PGA, we calculate that using the mean epsilon that we get from deaggregation data for the particular intensity measure that we're looking at, which is PGA in this case. And what you're doing is you're actually getting that probabilistic, the 2% and 50-year value, 0.58 G, you get the deaggregation for that value. That is what you want to use if you're doing a design based on a 2% and 50-year hazard level. Okay, and then you also can get your by knowing what the percentage of contribution from the different tectonic sources are, you can get your source-weighted mean sigma value, and using those, you can calculate your median PGA. Okay, so we've done that down here in this table, right? So there's your median epsilon that I showed you previously, percent contribution from each source, your mean sigma values, we showed that previously, and then these are the median PGA values you get, 0.24, 0.125, 0.15 for interface, and the total hazard is 0.175. Okay, so in the modified hybrid method, what we're doing in this particular example is we set the target spectrum to a 0.175 G. So this would be the median target spectrum, and it's scaled to, well, the median target spectrum is in red. That's coming from deaggregation of each of the hazard values, including PGA. And then what we're doing is we're scaling all of our time histories to 0.175 G PGA. Okay, so we get quite a range of ground motion values. The geometric mean of all of those is this solid black line. and then in gray is the arithmetic mean, okay? So we want to use the geometric mean because that's actually giving you the mean of the values when they're log normally distributed, okay? Because in this case, these values, if you plot them up, they would be, most hazard values are log normally distributed, and the time histories, as you can see, also look to be log normally distributed. So taking the geomean of that, same as taking the mean of the ln of all the values, just so we know. Okay. So now we're going to look at the results of the actual amplification factors that we calculate using both the simplified methods compared to the rigorous. So the blue one again is the amplification functions, amplification factors using the rigorous method. So these are the blue diamonds. We only have the values at the main code-based periods, 0.1, 0.2, 0.3 seconds, 0.5, 1 second, 2 seconds, etc. In our site response analysis, because we have essentially continuous amplification functions, we picked some of the intermediate values so we could better represent the actual peak, because this is such a sharp peak in amplification. So we have the modified hybrid method in green using the median for the total hazard of 0.175 G. And then in orange, we have another way that we ran this, where we actually did the scaling using the median target spectra for each of the source types, each of the tectonic regime types. And we got the individual F of T's that correspond to the 0.24 G for crustal, 0.125 for in-slab, and 0.15 G for interface. And then using the contribution weightings, we get a contribution weighted mean average amplification function, and that's shown by the orange circles here. They're very, very similar to what you get just using the median value for the total hazard. Although it's nice to look at, for time history selection, each of the individuals, for the actual calculation of amplification function, it doesn't matter whether you break them into the tectonic regime types or just use the total hazard. But now I want to draw your attention to the hybrid method. So this is like the NBC 2015 approach in red. It's not a coincidence I put it in red. So in this case, where you're basically doing the result, the analysis of the amplification function that would be generated if you had a PGAref of 0.58 G, this is the amplification function you get. Okay. So just like what we saw in the previous slide where I compared all the amplification functions together, what you see is a greatly reduced peak shifted from 0.3 seconds to 0.5 seconds, right? And rather than it being a 2.7 amplification factor, it's like 1.8, right? So it's significantly lower. And if we go to 0.3 seconds, it's almost like half of what we're predicting for using the modified hybrid method. Okay, so this is what's happening when we're doing site response analysis using the old way of scaling everything up to the total probabilistic hazard value, the stratospheric value. So now if we just look at what we get in terms of the amplified response spectrum, I'm just showing the modified hybrid in green using the median for the total hazard compared to the rigorous method in blue, and then the hybrid method in red. So it just happens to be coincidentally at this site that, like almost all of the different methods, because this is the VS30 code-based method in orange, we happen to get very similar values at 0.5 seconds, purely coincidentally. Okay, so be careful if you happen to do structural design based on 0.5 seconds and you go, oh wow, it doesn't matter what method you use, they all give the same result. Well, it's only at 0.5 seconds in this particular case. And depending on the period of your site, that's going to shift, right? Okay, so to summarize, in NBC 2015, we got amplification functions from the code. And there is different amplification functions for each site class. And the intensity measure for those amplification functions was a PGAref. And that is in Western Canada, PGAC, which is a probabilistic hazard value based on the aggregated hazard curve. Okay, so very high values. Since that PGA is so much higher than the PGA that would be associated with individual events, that amplification function tends to overpredict nonlinearity and damping. So it underpredicts the nonlinear amplification. And this has been pointed out in the paper by Michael Colli describing all the GMM models, right? In NBC 2020, the GMMs use site terms to estimate amplification of a rock ground motion value, which is a median prediction of the ground motion value for individual event scenarios. Okay, so then the linear amplification is relative to that rock reference condition, is calculated using the VS30 of the site, and then a nonlinear amplification is a function of that median prediction. It's most cases it's PGA. I think in one of the GMMs it's like SA.2 or something like that. But and then those amplified hazard values for each of the individual events are all aggregated probabilistically to give you your UHRS that you get when you go to the hazard calculator online. To do an SSRA compatible with NBC 2020, my recommendation moving forward is that you're going to, yes, assign your reference ground condition just like what we did before. We're going to develop a median target spectrum for that reference ground condition at the design hazard level that you're designing for, 2% 50 year or 5% or 10%, whatever the specified hazard level. And we're going to construct that median target spectrum using a full suite of site-specific deaggregation data, which correspond to whatever that designation you're using for your reference ground condition. And then we get that median value using this equation that I've shown and using the epsilon values that we get from the deaggregation values and the sigma values associated with the GMMs. Okay, so then when we do our time history selection, we're going to scale time histories specific to each of the three source types, right? But we're going to scale them to the median PGA specific to each of the tectonic regime types, preferably. And then you would use the geomean of that suite to see that it's close. This is just to make sure that you're getting time histories that are reasonably applicable for the tectonic regime that you're in and for the kind of range of ground motion values that you're expecting. Then you're going to take your input time histories, scale them to that median PGA for each of the target, each of the tectonic regime types, or you can just do what I showed you in the other slide, where you scale all the time histories for all three source types and scale them to just the median PGA that corresponds to the deaggregation of the total hazard. Either of these, as you saw, gives you pretty much the same result. It's kind of really which one you sort of prefer to do. Then you run the site response analysis, calculate the amplification function for each earthquake time history, right, which is just output divided by input. And then you develop the mean amplification function that you would get. And you do that for each of the tectonic regime types. And then you can weight those according to the percent contribution of each of the tectonic regime types to the intensity measure that you're using, which is PGA in this case. So you get those contributions from deaggregation and PGA. So you can also use the mean. My experience with this study was that there was very little difference between mean and geomean for the amplification function itself. At most periods. Okay, so which means it was the amplification function is more normally distributed. But if you took the mean, you're going to tend to be conservative. Geomean specifically is going to be more consistent with the logarithmic distributed framework where they calculate this. And then you basically just calculate, once you've got your average or your mean or your geomean amplification function, you calculate your amplified response spectra by taking that amplification function and multiplying it by the spectral values for your reference ground condition, right? This is just basically the modified hybrid method, or the hybrid method. You do that. It's just how you're getting amplification functions in this case that are specific to the median intensity level, not the aggregated probabilistic intensity level. I hope that made sense.